So on last Friday, we talked about inductors and inductance. So today we're going to talk about capacitors and capacitance. And I'm going to go through this material fairly quickly because you've effectively seen almost all of it before if you were here in class on Friday. So let's start with what a capacitor looks like. And they can come in numerous different forms, but they're all largely based on this single principle. So let's say that I have a conducting plate like so. So this would be some metal thing, and I'm going to unimaginatively call this my top plate. Well, that implies that there is some sort of bottom plate as well, which is going to be this guy down here. So I have two plates separated by some distance d, and I'm going to put an electrical lead on the top plate as well as the bottom plate to form what is called a parallel plate capacitor. Okay. So in a parallel plate capacitor, the capacitance C is defined as the permittivity epsilon multiplied by the cross-sectional area of the plates divided by the distance d between the plates. Okay. So the area of the plates is fairly straightforward. That's literally just the area of one of the plates. I've already defined the distance d separating the plates. So let's talk a moment about this permittivity epsilon. Okay. So permittivity of free space, epsilon naught, and you guys are not going to ever have to use this in this class, is 8.854 times 10 to the negative 14 farads per centimeter, where the farad is the unit of capacitance, and we'll sort that out in a moment. Okay. So what's going on here is effectively we have some medium that's physically separating our plates. This is called a dielectric. Many materials exhibit a dielectric constant that is roughly the same as vacuum. So epsilon naught is the permittivity constant for free space or a vacuum. Air is like 1.001 times that. Mineral oil is like 3.5 times that. Deionized water is like 81 times that. And depending on the material that you put between the plates, you can either have a larger or smaller capacitance. Okay. So let's talk about what's going on in this system. So if I were to apply a positive polarity of some voltage at the top plate and a negative polarity at some bottom plate, what do you guys think would happen? So I think electrons are going to get drawn off the top plate, leaving behind some charge, positive Q, on the top plate. And similarly, electrons are going to be attracted to the bottom plate, which means that we're going to have some negative charge down there. Now let's talk about this very briefly because this is something that we're actually going to kind of observe experimentally when we're looking at our transient analysis stuff. Okay. So instead of thinking about moving electrons off of the top plate, which is actually what's happening, let's think about if we were trying to put positive charge carriers onto the top plate. Okay. So for those of you guys that have had Physics 202, what happens when I try to put two positive charges near each other? They repel each other, okay? So effectively, for every electron that I pull off that top plate, or transversely every positive charge carrier I put on that top plate, it gets harder and harder to put the next one on because they're constantly trying to repel each other, right? So effectively, what I'm doing is I'm having to put energy in order to force that charge onto that plate, which is going to attract an equal and opposite charge on the other plate. And as long as I continue to transfer energy by applying a voltage drop across the capacitor, then I'm going to have some amount of energy stored because all those charge carriers are stuck in a position they don't want to be in. As soon as I lower the voltage, I'm going to allow that capacitor to discharge its stored energy into the system, okay? So for a capacitor, we have yet another energy storage element where the energy stored in this case is in the electric field that is sustained by keeping the charge separated, right? Or forcing more positive charge on the top plate and transversely negative charge on the bottom plate. Okay, so this is electric field lines. All right, so let's talk about things a little bit more here from a physics context, because this is a circuit component, and so we are expecting it in some way, shape, or form to be able to carry some amount of current, right? So my question to you guys is, how do I pass current through this component if there's literally a physical medium that isn't conductive, preventing current from flowing through it? So this goes back to what we were talking about a moment ago, right? Anytime I store charge on there, as soon as I start to discharge, that's going to cause those electrons to move, okay? So instead of having a traditional current that's flowing through the device, we're going to have what's called a displacement current, where electrons are just moving on and off the plate, and the opposite charge carriers are moving on and off the other plate, so that it seems like a net current is flowing through the device, okay? So we never physically pass electrons through the device as a whole. We're simply moving them on and off the plates, and that movement of charge on and off the plates behaves like a current. Okay, so let's write some things down here. So capacitors are a form of temporary energy storage in a circuit, okay? The energy is stored in the, excuse me, this should be electric field. Just had a brain fart there. Which is sustained by applying a voltage across the capacitor's terminals. So we are going to define capacitance mathematically, C, as simply the charge stored on one of the capacitor's plates divided by the voltage that's needed to move the charge onto that plate. So this is actually kind of similar to what we had when we were dealing with inductors, right? So we defined inductance mathematically as a ratio of magnetic flux divided by the current that causes the flux. Here we have charge divided by the voltage that effectively causes or accumulates the charge. So it's a very similar relationship, okay? So the units of capacitance are the farads. Actually, this should be lowercase f because we're talking about units and not the dude's name. So 1 farad, which has a symbol of capital F, is, according to this relationship right here, let's do it this way. It is going to be 1 amp second, where an amp second is nothing more than a fancy representation of a coulomb. Per volt. So this is effectively the same unit as we saw for Henry's, but the amps and the volts are interchanged. So we could also write this as 1 second per ohm if we were so inclined, but 99% of the time I use this amp second per volt relationship. So let me think about things here really quickly where I want to go from this. So we've talked about what capacitors are. Let's mention what capacitance is then. I don't think I've written that down yet. So capacitance represents a component's ability to react to a changing electric field. So again, we have something that's very similar to what we saw with inductance, where inductance was a response to a changing magnetic field. Capacitance is a response to a changing electric field, okay? Feel like I'm forgetting to mention something, but I can't think of what it is. So we'll move along from here, and when it pops into my head later, we'll sort it out. Okay. So let's talk about representing capacitances in circuits. So we're actually going to have 2 different schematic symbols, and a lot of people use them interchangeably. But because I am a nitpicky jerk, I do not, okay? Because they actually have very specific meanings. So the first one that I'm going to introduce to you guys is this guy right here. So effectively, it represents what a capacitor physically is: a set of parallel plates with electrical terminals connected to them. So we would represent the capacitance by some magnitude C. I'm going to represent some voltage drop across my capacitor terminals as V of T. And I'm going to say that my current I is flowing into the positive polarity terminal because we are once again dealing with a component that obeys the passive sign convention. Okay. So this is our general capacitor. And then the second one that you might see or may have already seen at some point is this guy, where we have one line and then a curved line like so. So here's C, here's V of T, and here's I of T. Okay. So this is what's called an electrolytic capacitor. And it's also known as a polarized capacitor. So in a general capacitor or generic capacitor, it does not care whether or not the voltage applied across it is positive or negative. But in an electrolytic capacitor, it does. If you accidentally apply the wrong polarity of voltage across an electrolytic capacitor, it will literally burst. Let me see if I can pull up a picture of an electrolytic capacitor really quickly so I can talk to you guys about this. I just wanted a bigger picture. That's a nice big picture. Okay. So this is a picture of an electrolytic capacitor. It's kind of hard to see because of the resolution on the projectors, but you might be able to see it better on the television screens. But notice at the top here, that is scored, right? So there's a big kind of plus size or plus sign pattern on there. That is literally to allow that top plate to mechanically deform, because when you apply the wrong polarity voltage across this, the chemical reaction occurs that generates a lot of pressure. And so if we didn't let that pressure bend that plate up there, the device would literally burst and spill toxic chemicals out of it. So that's almost kind of like a mechanical pressure relief valve. It's enough to let it deform without actually rupturing and causing further problems down the road and all of that kind of stuff. Okay. So that's an electrolytic capacitor. If you open up the power supply unit for your computers and most modern electronics and stuff, you're going to see things that look like that all over them. The reason why electrolytic capacitors are used in a lot of power supplies for computers and stuff is because even though we could plug our computer into a wall so that it technically runs off of AC, there is a device in there called a rectifier that is converting that that AC power into DC. So there should never be a negative polarity voltage across this because of the rectification of the AC signal. So this is a really good indicator of, hey, there's something wrong with my power supply if I ever see one of these burst, because somehow a negative voltage made its way through. So that's an indicator that the rectifier has failed. Okay. So that's why they're used. In contrast, these are a more generic non-polarized capacitance. These orange drop capacitors, as they're called, because it's literally just dropped in a vat of orange plastic or whatever, are very regularly used in the tone circuits for electric guitars and all of that kind of stuff, which is why I'm at a musical instrument supply website here. But you can also use orange drop capacitors for anything else as well. I just wanted to show you guys. So notice here, there is no marking or anything like that indicating a positive polarity terminal or anything. If we go back to the other one just real quick like, that silver strip is the negative polarity terminal, and then the black is the positive polarity terminal. So it literally indicates on the component itself which one to use as the positive polarity and which one to use as the negative polarity. Okay, so all of that to say, you will never see me use the electrolytic capacitor symbol in this class because every capacitor that we are going to be dealing with will be a generic capacitor because it would be too expensive to let you guys just play around with these and constantly burst them because you're not paying enough attention. Some people use these two symbols interchangeably. As far as the math and all of that kind of good stuff goes, it literally doesn't matter. But technically speaking, the flat line, curved line represents an electrolytic capacitor on a correctly drawn schematic diagram. So I just wanted to bring that to you guys' attention. All right, so now let's get into our current voltage relationships and all of that kind of good stuff. Okay. So let's call this circuit characteristics. So up here, or above, I just moved it off the screen, we have the relationship that C is equal to Q over V, which we could easily rearrange to say that Q is equal to C times V. Well, if I take the derivative of both sides of this relationship, so if my charge is able to change as a function of time, I would have dq by dt is equal to C times dV by dt, where I'm making an assumption here that my capacitance cannot change as a function of time, which, as far as we're concerned in this class, it can't. Okay. What is dq by dt, according to the second lecture we ever had in this class? You have notes. I told you where to look at them. Current. Exactly right. So current I of t is simply equal to capacitance times the derivative of the voltage. So this is our first equation. Let me put a box around it. Now, this should look very familiar. So on last Friday, I'm doing this in a different color, we learned that for an inductor, according to Faraday's law of induction, the voltage drop across an inductor V was equal to L times di by dt. So these two equations are literally the exact same thing, except that everywhere we saw voltage, we replaced it with current. Everywhere we saw current, we replaced it with voltage. Everywhere we saw inductance, we replaced it with capacitance. That will be true for every single one of the relationships that we developed on Friday. So there will be a capacitor relationship that is exactly identical, except that we'll swap current and voltage and replace L with C. So I'm not going to spend a lot of time deriving these today because we already know what those relationships are supposed to be. We can do something with this guy, much like we did with our inductor-based relationship, and think about how this element is going to behave in certain contexts, right? So if my voltage doesn't change with time, what's my current going to look like? Zero, right? So the derivative of a constant is zero. So I'll have C times zero is equal to I, so I must be zero. So that tells us that in a DC circuit, capacitors behave like what? What was that? So inductors behaved like a short circuit because we found that the voltage drop across them would be zero. So capacitors are going to behave like an open circuit because the current flowing through them must be zero. Okay. So after we looked at this relationship for inductors and found out that in a DC circuit, inductors behaved like a short circuit, we then worked an example problem where we dealt with a time varying current and saw what would happen if we allowed the current to change instantaneously, right? So that was our second kind of statement with regards to inductors. And we found out that in an inductor, a current cannot change abruptly. What do you guys think the similar relationship is going to be for a capacitor? The voltage cannot change abruptly for the exact same reasons, right? So the voltage drop across a capacitor cannot change abruptly. All right, so we have our derivative-based relationship. So now let me go ahead and give you guys our integral-based relationship. So this is going to be our second one. So the voltage drop across a capacitor is going to be equal to 1 over C times the integral from negative infinity to t prime dt prime, which is the same as 1 over c times the integral from t naught to t of I of t prime dt prime plus v at t naught. So there's our second relationship. Once again, we could get this simply by rearranging our derivative-based relationship and taking the integral of both sides. What do you guys think our power relationship is going to be? So always current times voltage. So if we take our first relationship for current as a function of voltage and substitute it into here, we wind up getting C times V times the derivative of the voltage with respect to time. So here's relationship number 3. And as I mentioned in class on Friday, 95+% of the time, I wind up just doing I times V. But every now and then, the C, V, dV by dt works a little bit better. Pretty rare. Okay. And then lastly, we had an expression for energy. I went through a derivation. I'm not going to bother with it this time because the derivation is literally the exact same thing as we had for the inductors, except that in this case, we will wind up with 1/2, excuse me, I forgot the C times the square of the voltage. All right, so those are our 4 relationships. They are the exact same relationships that we saw with inductors, except we're swapping current and voltage, replacing L with C. So the last thing that I want to talk about for today is how we can combine capacitors in a circuit into equivalent capacitances. So let's start with capacitors in series. So here I have some capacitor C1, some capacitor C2, all the way out to some capacitor C sub n, like so. I'm going to define the total voltage drop across all of those capacitors in series as V. And then I'm going to assign individual voltage drops to each capacitor. So this will be V1 of T, V2 of T, all the way out to Vn of T, like so. And because they're all connected in series, a common current flows through all of them. Applying Kirchhoff's voltage law around this loop, we would have our total voltage V is simply the sum of our individual capacitor voltages. We can use our integral-based relationship to express all of those capacitor voltages in terms of our common current I. So that would look like 1 over C1 times the integral from negative infinity to t of I of t prime dt prime plus 1 over C2 times the integral from negative infinity to t of I of t prime dt prime all the way out to 1 over C sub n times the integral from negative infinity to t of I of t prime dt prime. And now I can simply factor out that integral because it is common to everything, leaving me with 1 over C1 plus 1 over C2 all the way out to 1 over C sub n times the integral from negative infinity to t, bless you, I of t prime dt prime, or 1 over CEQ, integral from negative infinity to t, I of t prime dt prime, where CEQ is 1 over C1 plus 1 over C2, all the way out to 1 over C sub n, or 1 over the sum from I is equal to 1 to n of 1 over C sub I. In other words, capacitors in series combine like resistors in what? Parallel. So without making you guys suffer through the math, how do you guys think capacitors in parallel are going to combine? Like resistors in series. Okay, so I've covered the lecture material. I want to bring to your attention two web work problems, and I want to bring them to your attention for two reasons. One is that they're difficult. The other is that I like them, which means you should expect to see something like this on your upcoming exam. Okay. I'm giving you fair warning now. And these legitimately are two of the hardest homework problems that you guys are assigned. And it looks like I forgot to open it up, so I'll have to do that immediately after class. So I'll do that in the next couple of minutes. So if we look at problem 3 here, We have a circuit that contains a voltage source connected to an inductance, connected to a capacitance, all in series. So you are expected to be able to apply the necessary relationships based on what we've covered for the last couple of days, okay? So the ultimate goal in this particular problem is to find the source voltage if we're given the voltage drop across the capacitor. So we're having to work backwards a little bit here, okay? So let me put up a circuit similar to this. And let's talk our way through things. So here we have our voltage source. Here's an inductance. Here's some capacitance C. And we are told what VC as a function of time is. So let me just write VC of t is a known quantity, and Vs of t is what we're looking for. Let me see if there's any other information on here that we need or that we're given. Okay. Doesn't look like it, but that's okay. So let me ask you guys a quick question. What type of circuit is this? Think back for what we were looking at. Single loop circuit. Everything is connected in series, right? So whenever we had single loop circuits, way back in the first, second day of class or whatever it was, what did we use? Kirchhoff's voltage law. Okay. So in order to apply Kirchhoff's voltage law to this circuit, I'm going to have to assign a voltage drop across my inductor. So I'm going to do that as VL of t like so. And while I'm at it, I'm going to go ahead and assign a current that I'm just going to call I of t that's flowing around this single loop, right? So that current I of t is shared among all of those circuit elements because they're all connected in series. So if we were to apply Kirchhoff's voltage law to this system, we would find that Vs of t is equal to VL of t plus VC of t. Well, what is VL of t? L times the derivative of our current, right? So that's L di by dt plus our known capacitor voltage. Now, since we know the voltage drop across our capacitor, can we use that to get the current flowing in the circuit? Yes, because we know that I is equal to C dV by dt. So let me just do this as a quick aside over here. I'll do it in red since that's the thing I use for my current. Recall IC of t is C dV by dt. So I'm simply going to substitute that in for my current, and that's what's going to give me the relationship LC times the second derivative of my capacitor voltage with respect to time plus VC. So it's not actually all that hard. We just have to be able to apply those relationships that I've shown to you guys, right? So let's look at another one. This one is going to be similar to homework 12, problem 5. So in homework 12, problem 5, if I'm remembering correctly, I believe that I am, we are given some voltage source, Vs of t, and then we have a capacitance C connected in parallel to some inductance L. And our ultimate goal is to figure out the current that is being supplied by our source. So we're given a few different things, right? So Vs of t is a known quantity. And if I'm remembering correctly, Is explicitly at t is equal to 0 is also a known quantity. And once again, we're trying to solve for Is as a function of time. So what type of circuit is this? Single node pair, absolutely right. Where in a single node pair circuit, all of the elements are connected in parallel. How did we approach every single node pair circuit? Kirchhoff's current law, okay? So I'm going to define a current IC of t like so, and a current IL of t like so. And applying Kirchhoff's current law to this system, we would find that Is of t has to be simply the sum of IC of t and IL of t. So how do we get IC of t if we know what the voltage drop across the capacitor is? We did it right here, right? So IC is just C times, in this case, the derivative of the source voltage with respect to time. So we would have C d Vs by dt. How do we get inductor current if we know what the voltage drop across the inductor is? That's the integral-based relationship. So that would be 1 over L times the integral from T naught to T of Vs of T prime dt prime plus IL at, let's say 0 here for our T naught. So the reason why I'm choosing 0 for T naught is because I know what my source current is at T is equal to 0. So that's giving me a strong hint, okay? So if I look at this expression, since Vs is a known quantity, I can take the derivative of it pretty easily. And again, since Vs is a known quantity, I can probably integrate it pretty easily, okay? So the only thing that we don't currently know is what my inductor current is doing at exactly T is equal to 0. Instead, I was given what my source current is doing at T is equal to 0. Can any of you guys think about how I might be able to figure out what my inductor current was doing at 0? So that's definitely going to have part of it. So let's follow Ashton's thing here, right? So it stands to reason, according to Kirchhoff's current law, that if we know Is at 0, that has to be the same as IC at 0 plus IL at 0. Because Kirchhoff's current law has to be satisfied at literally all points in time. Can't not be, or we're violating laws of physics, okay? Well, Is at 0 is a known quantity. IL at 0 is what we're looking for. So how do we find IC at 0? We literally just evaluate this thing at t is equal to 0. So we could rearrange this to find that IL at 0 is equal to IS at 0 minus C dVs by dt evaluated at t is equal to 0. And then we have all of the different parts that would go into our expression for IS. Once again, nothing wildly difficult here other than needing to know how to apply all of those relationships that I've thrown at you, right? So I've given you guys some extraordinarily strong hints on how to work those two problems. This is just me trying to head you guys off at the pass so that I don't spend all my office hours for the next week answering literally these questions. All right. In-class assignment, do it up. Let me get the web work assigned and all of that kind of jazz.